All right, to kick off chapter 6, lesson 6.1, talking about exponential growth and decay functions. So exponential functions take this form like you see here, y equals a times b to the x power. This having exponent of a variable is what makes it exponential. Your a value cannot be 0, and your b value can be any real number other than 1, any positive real number other than 1. So we have a couple of different things that happen with exponential functions. Right? So our first case here is if your a value, that initial value, is greater than 0, and your b value is also greater than 0, then your function is what is called an exponential growth function. So some things that might have exponential growth in real life would be population, population of people, population of animals, bacteria growth, bank accounts can all have exponential growth. And if you have exponential growth and your b value is greater than 1, then that b value can be called a growth factor. If your a value, for our second thing that can happen, our a value has to be greater than 0. If our b value is between 0 and 1, then we get what is called an exponential decay function. Exponential decay can happen, again, in population of different things. It can happen in isotopes, the radioactivity of materials, things like that. And when you have that, your b value that's between 0 and 1 is called the decay factor instead of the growth factor. So here are the parent functions for exponential growth. Right, we have our exponential growth function on the left, and the function f of x equals b to the x power, where b is greater than 1, is the parent function for the family of exponential growth functions. We see here that it has an asymptote right here. So my y values, my outputs, will approach a value. In this case, it's 0, but never actually touch. So the parent function has a range of y is greater than 0 because of this right here, where it approaches 0 but never actually touches it. The domain of all of our exponential functions is going to be all real numbers. Right? We see that they continue on, the x values continue on forever and ever in both directions. On the right side, we have an example of a decay function. Our b value then has to be between 0 and 1. They still have that asymptote right here that impacts our range. Right? So again, domain is all real numbers. Our range is y is greater than whatever that asymptote is, in this case 0. So we use our graphing calculators to graph these functions. The easiest way to deal with these, just go to y equals and you type in whatever that function is. So our first example is 2 to the x power. Okay, so I type that in. I can hit graph to get an idea of what the picture is going to look like, my graph is going to look like, but ultimately I need the data, so I'm going to go to second table. And on our paper, on the slides here, our table has already got some x values filled in, so I am just going to make sure then that I am using the table to enter the data. So we get 0.5, and then 1, 2, and 4. Right, so all of that just comes from my graphing calculator, and then I can use the data to make my graph. Right, I have a point there, over 0, up 1, over 2, up 4. Right, so I see something like that. I see that good exponential growth, which makes sense because my b value here is greater than 1. In example B, we have a B value that is between 0 and 1. So that tells me I'm going to have some exponential decay. And I'm going to just enter that function into y equals on my calculator, 1/2 to the x power. If I hit graph, I get the picture. I see the exponential decay happening. And I can go to table then to get my values. Right, so -2, 4, -1, 2, 0.5, and this would be a 1 here, and then 0.5. Right, so I come in, I graph it up, and I bring my line to show that exponential decay. Right, so again, just enter whatever that function is into y1 on your calculator. So looking at exponential models, these are used in real life for different things. A lot of times for predicting counts or populations, those sorts of things. So we see the exponential growth model highlighted here. Right, so A is your initial value, and then 1 plus your rate of growth. As a decimal, you're going to change that percentage to a decimal, and then the T is your amount of time, typically years. And then exponential decay, the only difference is we still have that initial value 1, and then we subtract whatever your rate of decay is. And again, you need to change any percentages to a decimal. We take that value then to the T power before it gets multiplied by that original, right? So order of operations takes care. We do this addition or subtraction to find our growth or decay factor, and then we take that to the exponent before we multiply it by the original value. So here's an example that we can look at. The value of a car in thousands of dollars can be approximated by the model y equals 25 times 0.85 to the T power. T is the number of years since the car was purchased. We're supposed to determine whether this is going to be an exponential growth or exponential decay model. And we could graph that to get that. Or we can look right here. We see that our B value is 0.85. So that's between 0 and 1, which is going to give us exponential decay. Okay? Part B, identify the annual percent increase or decrease in the value of the car. So our decay factor is the 0.85. So each year, our car will be worth 85% or 0.85 what it was the previous year. So the amount of decrease would be 100% minus the 85% for 15% or 0.15 out of 100. And then they want to know when will the car be worth approximately $8,000. So in our initial, this 25 is in thousands of dollars. We see that here. So we would want to set up on our calculator any sort of or some sort of equation. We would type in the 25 times the 0.85 to the x power, right? And remember that 25 is in thousands of dollars. So I want to know then when that model is going to be worth 8, representing the $8,000. So I can go to table. I see that my car is originally worth $25,000. I can scroll down. After 5 years, it's worth about $11,000. 6 years, about $9,000. So after 7 years, it's worth about $8,014. So if we scroll down to 8 years, it drops down to just under $7,000. So my answer here would be at about 7 years. Since it says estimate, we can just use the table. If we needed to be more precise than that, we could go to the graph. We could use the intersection tool if we needed to. But since it says estimate, that at about 7 years is perfect. So in example 3, it says in 2015, the world population was about 7.38 billion. During the next 5 years, the world population increased by about 1.09% each year. Write an exponential model that represents the population Y in billions T years after 2015, and then we are supposed to estimate the world population in 2020. So our equation would look like this. We'd have Y equals, and then for these exponential models, you always start with your initial value. So 7.38, that's in billions. We're not going to write out all the zeros. We're just going to keep in mind as we work this that is in billions of people. And then they tell us that the population is going to increase by about 1.09%. So since this is growth, right, we're going to go 1 plus, and we're going to write that 1.09% as a decimal. So we're going to scoot the decimal 2 places to the left. So that would be 0.109. And then our exponent then is going to be T years after 2015. So that is our exponential model. And then we are to estimate the world population in 2020, right? So we're going to take that 7.38 billion, and we are going to multiply it by 1.0109. That's our growth rate there, to the 5th power, because 2020 would be 5 years after 2015. This becomes a calculator problem, so we will get this punched into the calculator. Right, so 7.38 billion, and then times 1.0109 to the 5th power. Right, so that's going to be what we plug into the calculator. So they're telling us in 2020, the population would be about 7.79 billion people. Right, we'll throw that label on there instead of writing out all the zeros. So that's our estimate for the population. So one important thing that these exponential functions can be used for is calculating compound interest, right? So compound interest is interest paid on an initial investment called the principal on a previously earned and on previously earned interest. Interest earned is often expressed as an annual percent, but the interest is usually compounded more often than once per year. So the exponential growth model of y equals that initial a times 1 plus r to the t must be modified a bit to compound for compound interest problems, right? So this formula here works great if it's compounded annually, but the world doesn't usually work that way. Banking doesn't usually work that way. So down here in the blue box, we have compound interest, right? So you have that P, your initial principal is what you deposit into an account or invest, and then your annual rate is here at R. We're going to change that to a decimal, of course, not as a percent. And then we get a new value here, the N value. That is how many times a year the interest is compounded. A lot of bank accounts compound monthly, some quarterly, but monthly is a pretty popular how often a compound time period. And then we have the t still in years. Notice our exponent now changes to n times t. So we are going to take our p initial principal and then multiply that by 1 plus our interest rate divided by our n value, and our exponent becomes n times t. So let's look at this in a real world example. We're going to deposit $9,000 into an account that pays 1.46% annual interest, finding the balance after 3 years when the interest is compounded quarterly. So we're going to start off here with that compound interest formula. We don't know A. That's what we're trying to figure out, how much we have in our account after 3 years. So our principal is 9,000 times 1 plus our interest rate, which would be 1.46%, so 0.0146, right? Make sure you change that over to decimal form, divided by n. Quarterly means 4 times per year, right? So we're going to divide that interest rate by 4, and then our exponent is going to be n times t, so 4 times 3 years. So that means in the span that we are looking at, we're going to get 12 interest payments, right? This is going to become a 12 here, and then 1 plus 0.0146 over 4, right? And so from here on out, we're going to be looking at doing some calculator work, right? So I'm going to start by cleaning up this fraction here. So I'm going to enter that into the calculator, 0.0146 divided by 4. Okay, I'm going to add the 1 to that. Right, so I get 9,000 times 1.00365 to the 12 power. Typically, we round to 3 decimal places, but when you're dealing with this finance stuff, this is going to change your outcome by not rounding. So ultimately, I would just keep working in the calculator, right? So I did the division, then I just hit the +1, and now I'm going to hit the caret, right? And if I needed to multiply here, I could put parentheses. I could have done the 4 times 3 right here, right? You're going to do a homework problem, I think, where it's compounded daily, so you're going to have a bigger number there at 365 times how many years, right? But we could do the 4 times 3, and we make that a 12. And then that is what is in the parentheses then, and then we're going to multiply that by 9,000. So after those 3 years, we have $9,402.21. Right, so there's my answer. Okay, so that's my value in my account after the 3 years. So there was your introduction to exponential growth and decay functions. We looked at graphing them and a little bit about how we can use them to calculate populations or whatever it may be using exponential functions, and then we ended up with the compound interest formula. That's probably one that you'll use the most in real life, maybe in work or something, to find value after a set amount of time based on an interest rate.